try
Huh?
written information on our head wall can try and go out with the mouse.
You're adversely affected by the weather. Alright. Right, so we're going to continue with the equations that we had a look at yesterday. And this time we're going to have not the game.
I know this.
Yeah.
But I didn't understand the
No. Half-life.
You don't get a full chance in physics.
No. Right, have you got this half-life? Yeah.
July 20, 2006.
Okay. Right, so you know from the class yesterday that n equals n0 e minus lambda t. We also know from maths class what this graph looks like. So you remember from maths class, it'll be exponentially decreasing graph. So it will look something like this. You know this from maths class. This type of graph will look like this.
Yeah.
We did a lesson on these graphs in semester 1. Yeah. So there's nothing special there. You know this already, or you should know this. That should not say uranium up the top. That's not uranium, that's a graph. Right, what is interesting about these graphs is that the time required for half of the sample to decay is the same regardless of when we look at the sample. So, for example, here, well, you know what, actually I'll give you some data. So some sample data will make this clearer. So for example, here's some data where T is time in seconds and N is the number of atoms in moles. So when time is 0, we have 100 moles. 2 seconds later, we have 50 moles. 2 seconds later again, we have 25 moles. 2 seconds later again, we have 12.5. So every 2 seconds, what happens? We have the number of atoms remaining. And it doesn't matter where we start. So for example, if I start at 4 seconds, if I start here, 2 seconds later I still have half. Or if I start at 8 seconds, 2 seconds later I still have half. Yeah? So this is an important idea, that the time to half the sample, it doesn't matter when you start, the same amount of time will need to pass to half the sample.
Even if you try like odd numbers?
Yeah, it doesn't matter where you start. So this gives us the concept of half-life. You know what, actually, I would like you to write this table down, and what I want you to do is to draw little arrows every time it halves. So you can do like half, 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 and half, and half.
Just the table number now?
Just the table, please. Huh? The whole table, and then highlight every time it halves. That T should be a small t, but it doesn't matter. Yeah. Got it? Yeah.
Number 10 is half.
Huh?
Number 10.
Number 10?
Yeah.
What do you mean?
So now it's 86.25, which is half. 10 half. Yeah, this.
What are you talking about? 10? This is half of this number.
Yeah, it's half.
Yeah. Okay, continue. Right, so this gives us the concept of half-life. So the half-life of a radioactive sample is defined as the time required for exactly half the sample to become non-radioactive or stable. So in other words, the time to lose 50% of the radioactive material.
So if you write an example, half-life for example, is time to lose 50% of the reactive material.
Yeah, except the only thing that put me off maybe is the word lose. I guess it is lose, but it's not like it's gone, it's just become a stable material. Like for example, the sodium 24 became, part of it became magnesium, which is not radioactive. I suppose this is fine. Okay. Got that? Yep. Okay. Right. So let's have a look at the formula for the proof. Proof is quite straightforward. We have n equal n0 e. I think this proof came up on the exam once. There's not many proofs on the exam. I'm trying to think. What was the last proof? Can't even remember. They don't come up that much, but I think I remember seeing this once, maybe. So it's not a difficult proof. What you do is you say you want half the amount of radioactive material. Right, so we can cancel them, and we have 0.5, or a half if you want, equals E minus lambda T. We put a log on both sides, and we get log 1 minus log 2 equals minus lambda T. Do I have log 2 or log? Yeah, I do. So this will be 0 minus log 2 equals minus lambda T. So then T equals log 2 over lambda. And because this is the time for half of the material to remain radioactive, we usually put something down the bottom here, like the word half, like half-life time or something. Nope. Now, what was the unit for lambda decay constant? I know, the other way I prefer. S minus 1 per second. So what unit is log 2 over lambda? What's 1 over seconds? Seconds.
Yeah.
Which makes sense because it should be a time. So this is the formula to calculate the half-life. Yeah? Short enough proof. Oh, I remember what the other proof was. It was on the lesson with the electricity. Yes. Hey, who are you looking for?
Yourself.
Oh. Thank you. We're just missing Yemi. We don't know where he is, do we? Is this your first class today? Yeah.
Alright, guys, I've heard you're not really working
physics hard enough.
I think that's fair. Everybody's working at different levels, but myself and Connell are concerned that there's not enough work being done for physics. After all, your test is next month. Not only is your test next month, you already have the timetable for the test, which should make it feel very real. Yeah. So myself and Connell now will be watching things carefully.
Or the predicted grades might be revised downwards.
Yes, it can only go downwards. So we're not happy, okay? But you know you're not doing enough study. You know this. Anyways, Connell might talk to you individually in tutorial, okay? But we're watching things. Yeah. Alright. Now I remember the other proof that we had, it was on the lesson with electricity, where we had to prove, do you remember with the graph with the logs in it, and we had to prove, what was it? Yeah, it was RC, wasn't it? Yes, that the slope, that was it, that the slope equals minus 1 over RC, wasn't it? I can't remember right now exactly what the proof was, but there was one other proof I do remember. Anyways, back here, so this is the formula. I mean, I write it like this, but I think in the formula book they might write it like this: lambda t a half equals log 2. It doesn't matter, it's the same thing. So this is the formula for it, the half-life formula, which you have. So let's have a look at a question. The isotope carbon-14 has a half-life of 5,730 years. 5,730 years. Now you can if you want, but if you're careful you can avoid that. As long as your time stays as years throughout the question. What is the lol? What's the half-life in seconds? Yeah. Actually, that's funny. Hope we don't have to change in seconds. Yeah, well, you do.
Because you know state whether it was a leap year or not.
We shall not worry about that.
Changing it 3 blocks.
Can everybody change that into seconds, please? 5,730 into seconds. Yeah. 5,730.
Years.
What?
So we're going to use an average of 365 days.
Yes. Where's the uranium, not uranium. And there was something else I wanted to change, wasn't there?
The opposite seconds here.
What?
The years into seconds.
No, some other problem with the last worksheet. Was it a unit?
75 billion seconds.
Good, sounds good.
No, I got 1.8 times 10 to the 11 seconds.
I'll do it now. There was some other mistake, wasn't there? I have uranium instead.
Yeah.
Oh yeah, small t. That's what I wanted to change.
Table.
In the table.
Where is the table?
There it is. Right, okay. Right, so let's have a look here. 5730 times 365 times 24 times 3,600. So what did you get, KJ?
1.8 times 10 to the 11.
That's it. What did you get?
How did you do it?
Really? 5730 multiply 365 multiply 24 multiply 3,600. Right? Yes? A. B. What is the decay constant? Now, you can use your new formula. that the half-life time, what is that? Log 2 over lambda. And this actually is the half-life time. It's the half-life. So actually I should put a little half here. So therefore lambda equals log 2 over the half-life time. So you get a tiny number, 3.84 times 10 to the minus 12 per second. Now that should say 14 grams. So I'm telling you the molar mass of C14 is about 14 grams. How many moles are in a 100 gram sample? Well, that's easy peasy. What's that? How many moles? 7.14 moles. Yeah. There's a 100 gram sample and carbon 14 has a molar mass of about 14 grams. Carbon 14 will decay into nitrogen 14. Although I don't ask you for the equation, let's write it down. Look. Carbon 14 is this. What's carbon? 6, isn't it?
Yeah.
And what's nitrogen?
5.
5, is it? So what type of radiation is coming out of carbon 14 to balance this equation?
Beta.
Yeah, it must be a beta, mustn't it? No. Absolutely, no, definitely not. Because this is a 5. So we must have here like a helium. But this will make the top too big. It's one of these things where we have so many heliums and so many betas. I don't know how many, I'll just write X and Y here. So you have alpha and beta coming off of the carbon 14. Will we calculate it? It's not going to be too difficult to calculate, I don't think.
It's going to be 0.
For what?
Correct.
No.
14 minus 14?
It's 0. Yeah. So
0 minus 0 divided by minus 4?
What about the Y part?
Y is 0.
Yeah, so down the bottom, not the top. Yes?
So minus 1.
Oh, sorry, the minus 1 is down the bottom. Thank you, Tekken. Let's calculate for the fun of it. So we should have 14 equals 14 plus 4x, and then 6 should equal 5 plus 2x minus y. You're right, Fahad. So x should be 0. So then, what does that make y then? 1. Now, less than, it's fine to have fractions here. I'll fix that in a second. 6 minus 5 is 1. Oh, it's
So minus 1.
minus 1.
Yeah, minus 1.
That's no good.
No, when you instead of the beta to be minus 1, it's adding 1.
Yeah, there's something wrong here. I don't think it becomes.
Maybe, no, we don't know the value of gamma.
It shouldn't affect it. All right. Maybe that was a good reason I didn't ask you to do this. So we won't do it then.
So what did you ask?
So what did I ask? How long until you have 25 grams? Right. How long until you have 25 grams? Now you can actually do this one really quickly if you think about it.
Use the mass formula.
No? How many grams do you have at the start? 100. And you want to know when we have 25 grams?
We can use the M0 formula.
No, 25.
So half
Take the
minus
half-life
minus
twice.
It halves twice.
Minus 5.
So to go from 100 grams to 50 grams is one half-life, and then 50 grams to 25 grams is another half-life. So you have two half-lives. So it's going to be 22,920 years.
You won't get it.
What do you mean?
Like he asked for 1 gram.
No, that was part E. Part D is 25 grams.
Okay.
Yeah, now part E is 1 gram. So, for part...
2. So what you multiply by 2 half-life?
2 half-lives, isn't it? Maybe
Five,
hang on, 573, or maybe I mistyped it.
Yeah.
Sorry, it's not that number, it's 11460 years. Thank you. Okay. E. We want to know when we'll have 1 gram. So we can use this formula. 1 gram equals 100 grams E minus lambda T. Okay. So 1 divided by 100 log of this divided by minus 1. And what was my lambda?
Lambda.
Yeah, was 3.8. 3.84 times 10 power minus 12. Yeah? So I'm going to get a huge time in seconds. Let's make it hours. That's hours. Let's make it days. Let's make it years. 38,000 years. Approximate. Yep. So it takes a very long time for 100 grams of uranium to become only 1 gram of uranium.
That wasn't like uranium.
Huh?
That was uranium.
This was uranium, wasn't it? Uranium. Oh, sorry, not uranium. This was carbon 14. So it takes a very long time for carbon 14 to become.
Because the whole periodic table is based on they compare the values by carbon. Because that's not
Yeah,
the
carbon
real value.
12.
Yeah.
Yeah.
Because they compare it. That's not the real value, but they just assume and compare it to other values.
Compared to carbon.
Even uranium takes more or less?
Huh?
Uranium.
My what?
Uranium.
Uranium is. I don't remember. It's. No, I think it's pretty big. Maybe not as big as carbon.
Yeah, no.
The carbon
It's on the scale of years still. Carbon is pretty big though.
Yes, it's the most.
Because that's what they use to find the animals.
Yeah, to dating, yeah. Right, okay. Now, just a sec.
One more?
No, hang on, don't confuse me. There was something I remembered, now I forgot. Oh yeah, it was with... No, don't pack up. We're going to have a double class.
No, we don't have a double.
Yeah, I know. I'm taking a double class now. You're free in the next hour. So, I'm taking you for a double class.
I'm just thinking that.
What? You need it. One.
But we won't have any break after this. We don't have any break.
She only started at 11 o'clock.
I didn't make anything.
I'll give you a 5-minute break to get some food if you want.
I have to do math.
I'm going to do maths next.
Do math.
Have double math.
I know you do. I'm not sure what your point is.
I came like around 9 to 30.
Good for you. After this class, what do you have at 1 o'clock?
We have EAP. We need to do.
Wait, don't you have individual tutorial with Connell?
No, not
No?
today. Not today.
So what do you have at 1 o'clock?
We have EAP. We have to do presentation, like prepared presentation.
Okay, and at 2 o'clock?
Same.
Okay, and then 3 o'clock?
Maths.
Maths. So how about this for you? If we do a maths now, then we will only have 1 maths later today. You can leave earlier.
No, that's actually, I don't mind. We can start.
So you can leave, you can go home at 4 o'clock instead of 5 o'clock. And I'll give you a few minutes to get some food now if you
Why
want.
don't you get the group tutorial time?
So we don't have a group.
Later.
No.
We have individual.
Individual, sorry, individual. We don't
We
have
don't-
individual.
We don't have individual today.
We don't have individual.
You don't have individual
No.
at 1 o'clock.
No.
So you're free at this time.
No.
Only this 3 hours. We have 3 on the time.
How is this?
So you have lunch at 1 o'clock.
No.
You're,
No, we have EAP. One.
are you in class?
Yeah. It's
Ah, okay. Your individual tutorials converted into
No, we
EAP.
don't have individual today.
Oh, whatever, group tutorial, whatever.
No, we don't have any.
No,
No tutorials today.
So yesterday.
So how come you have 3 hours of EAP?
2 hours EAP, 2 hours of math.
Oh, this is normal.
Yeah.
Okay, fine.
It's just
Yeah. It's not- Right, well look, do you want to go get some food, come back, and this way you can have a single maths task later today? Or do you want to take the break now and then have a double maths later? It doesn't matter, I thought I was doing you a favour.
Okay, I'll get something, please.
Yeah, that's fine. Do you want to grab a sandwich and come back? This way you can leave earlier. Unless you want to be free now and then leave at 5. I mean, that's fine also.
Do you want any drink?
No, I'm okay actually. I'm good, thank you. Seriously, no thanks.
Are you
It's cool.
sure?
I have my free coffee here.
With marshmallows?
I can do
Cherries on top.
It's all cool. It's all cool. It's all cool. Thanks. No, it's okay.